We're going to do some examples that are similar to section 1.7 in the textbook, combining functions. So we have a function here, f, and it's defined as a set of points, -1, 2, 0, 3, 1, 1, 2, -1, 3, 1, and g, which is also defined as a set of points, 0, 1, 1, 2, 3, 2, and 4, 1. Find, first of all, f plus g. So f plus g means we have to add the points of f to the points of g. And the key thing here is the domain of this function, the domain of f plus g, is the set of points where there are x values in f and x values in g, where the x values match up. So the domain, this will help us to understand what to do. The domain is it -1? There's a -1 in f. Is there a -1 in g? No. So not -1. 0, 0. They both have x equals 0. 1, 1. Okay, 1's in the domain. 2, oh, there's no 2 in g, so 2's not in the domain. 3, 3. Okay, and 4, there's no 4 in f, so 4 is not in the domain. Okay, so that's the domain for f plus g. It would also be the domain for f times g, because you can only combine the functions for x values that exist for both of the functions. Let's just get a quick idea of what this is like graphically. I think I'm going to have to move this down a little bit and need a little bit more space. Okay, so I will do f in red. So f is -1, -2, 0, 3, 1, 1, 2, -1, 3, 1. So you can see these points. And g is, I'll do it in green, 0, 1, 1, 2. There's no values for 2, 3, 2, and 4, 1. Now, we could also figure out the answer graphically. All we have to do is add the y values. If they both have a point for a certain x value, then we add the y values. So here for 0, 1 plus 3 is 4. So we're saying that this color blue is f plus g. Just to make a little legend to help you out. Okay, for x equals 1, we have y values of 0 and y values of 2, so 0 plus 2 is 2. I'm just going to go like this so you can see both points. 2 is not in the domain because I have a point for f but no point for g, so moving on. Oh, for 3, it is in the domain. 1 plus 2 is 3. And 4 is not in the domain of f plus g. So we can see from this that f plus g is equal to a set of 3 points, 0, 4, 1, 2, and 3, 3. This should be the exact same as what I would get if I looked at the function and if I figured out I just added these y values. Zeros, 3 plus 1 is 4, and for the ones, 1 plus 2 is 3. Uh-oh, did I make a mistake when I graphed it or when I read my graph out? 0, 1, and 1. I made a mistake graphing this. So I should have had this red one instead of it being here, I should have had it here. Which means my blue one was not here, it would be here. And so 2, I should have 3. Suppose if you approach something from more than one strategy, then you can find mistakes that you've made. So if I've solved a problem graphically and I just check it algebraically, numerically in this way, then I found my mistake. If I only did the question one way, how do I know that I'm right? I usually try to do every question more than one way. Okay, 2, there's no 2 in the domain, so 3. 2 plus 1, 2 plus 1 is 3. Okay, perfect. So I went over my work and I checked it. I know that it's right. Perfect. We can use the same approach to find f times g. So that was the question part B. This means f times g. You could also write this in different notation, like you could do f times g. We don't really like doing f times g like this so much because it can look like multiplication, but sometimes in textbooks they will use it if their font is very clear. You can make the primes that looks a little bit different than the x, but mostly people prefer just doing fg or like this. Okay, so in purple I'll do it graphically. But remember, my graphically didn't turn out perfect. So again, it has the same domain. So I just need to look at 0, at x equals 0, x equals 1, x equals 3. I won't bother looking at the other points. So my y values were 1 for g and 3 for f. 1 times 3 is 3. So f times g is here at 3. And 1... it's a little messy now, but I did have a green point here, I believe. Let's check 1 and 2. Yeah, green point here. So we have 1 times 2, which should be 2. Maybe I jumped ahead last time and did multiplication a little early. Sometimes our brains do silly things like that. Okay, and then for 3, again we have 1 and 2, it looks like. Let's see. I'll double check the values right here. 1 and 2. Yep, so 1 times 2 is 2. So looking at it graphically, I see f times g is equal to 0, 3, 1, 2, and 3, 2. You can double check that by looking at the points. Zeros, 3 times 1 is 3, good. For the x value of 1 times 2 is 2, great. 1 times 2 is 2, good. So I agree with this one too, I will check it out. If I was doing this in my homework, you can put check marks beside to show that you've done that you checked your work. It'll show me that you feel confident and you've done all the right things. We could be given a graph and we can be asked to make new functions with it. We could do f plus g. You know what, I just did an f plus g. Let's do an f minus g. So you can see what that would look like. Same idea, you're just subtracting. So again, if these were lines that continued forever in each direction, then you could find as many points as you possibly could. If these were graphs that had endpoints, you would have to only include parts where they overlap. So how should we approach this? Let's say that these lines are just line segments and they end. So in that case, we can only start adding points here, because even though g at x exists from -4 to -2, f at x does not. So we can only start at this point. So at x equals -2, we have f, the y value for f is 5, and the y value for g is -2. So we have 5 minus negative 2. Careful with your double negatives. Never hurts to write it out so that you don't make a silly mistake. 7. Oh well, 7's not really on my graph, but I'll just add it there and hopefully that works out fine. Okay, so the next set of points are, it's going to be a solid line. I don't need to put every single little point. I'm just going to do the ones that are easy to read off of the graph. So let's do x equals negative 1, which is exactly the next one anyway. So 3 minus negative 1 is equal to 3 plus 1 is equal to 4. The 0, x equals 0, we have 1 minus 1 is 0. Okay, so I've already noticed that I've made a mistake. Mistakes happen, that's okay. Catching the mistakes is what's important. So I said that we had 3 minus negative 1. And then I'm looking at the shape. I know that something linear plus or minus something linear gives us something linear because we haven't multiplied any x's. So we haven't gotten an x to the power of 2 or anything else. Linear plus linear is linear. And yet I see my slope went from being like minus 3 to suddenly being minus 4. I've made a mistake. So if I look at this carefully, yeah, that's pretty much explaining the problem here. So it's not the y value that's negative 1, it's the x value that's negative 1. I was silly here, it should be 3 minus 0. So I picked the wrong y value here off the graph. I've seen students do that before. Sometimes that happens. You just need a method to find your mistakes and correct them. That's the important thing. So, the point should be there. Now that looks better because I'm going down 1, 2, 3, 4 over 1. Down 3 over 1. And I'm really silly and I made the exact same mistake here. Maybe I should just restart this section of the video completely. I think that's what I'm going to do. Okay, now let's find f minus g. So again, f minus g is only going to exist where f at x and g at x exist. We could be given lines that continue forever in either direction, in which case the function that it makes will continue forever in each direction. Let's suppose that these are actually just line segments and that f at x only exists from negative 2 to 2.5 and the domain of g at x only exists for negative 4 to 3.5. So I'll just write out that domain f, x is greater than or equal to negative 2, less than or equal to 2.5. So the domain of f minus g has to be the set of x values that are both in f and also in g. So from 2 to 2.5, we have points on the graphs for both. Another way we can express the in general with the domain is that the domain of f minus g is equal to the intersection, or the intersection of the domain of f and domain of g. We don't use this notation as much in high school, but we're starting to show intersection and union, and you'll learn about it more later on. So this just means what you've seen here, that the values have to be in f, and in the domain of f, and the values have to be in the domain of g, for them to be in the domain of f minus g. Okay, so let's start figuring out some points here for f minus g. So here's a point here and a point here. The y values, I'll write them out so hopefully I won't make any silly mistakes. The y values are positive 5. This is at x is equal to negative 2. 5, and the y value here is negative 1. So 5 minus negative 1, which is equal to 5 plus 1, which is equal to 6. Okay, so that's the first point. And we could skip along and just do 2 or 3 points, or we could choose to do every point. The advantage of doing a few extra points is if your line is a little bit off, you'll see you're making a mistake and you can fix it. The first time I tried to do this, make a little video, I made a silly mistake, and I started adding y values and x values. It was really silly, and I was getting something that wasn't linear, and right away I knew it wasn't the answer, because linear plus linear has to equal linear, or linear minus linear has to equal linear, because the only way we can stop having an exponent of 1 would be to multiply. If I'm adding x values, I just get a line with a different slope. Okay? So, that's just an example, and it's not exactly the line we have in this situation. Okay, so let's do x equals negative 1. So we have a y value 3 for f, and we're doing f minus g, so now we're subtracting a y value of 0. 3 minus 0 is equal to 3. Okay. In this case, we have 1 minus 1. F is equal to 1, g is equal to 1, and we end up with 0. Next point, now you have to be careful here, you can't just do top minus bottom, because we're doing f, the blue one, minus g, the green one. So we have, I'm going to write it out so I don't make a mistake, negative 1, subtract 2 is equal to minus 3. And now we can start just checking that this makes sense. Look, we have a constant slope. So we're going down 3 over 1, down 3 over 1, down 3 over 1. That makes me feel fairly confident. I can draw the line. And this line would sort of continue to about here, because the domain of f minus g continues to 2.5. This is called f minus g. Okay, you could also multiply. You can use the same strategy to multiply. I'm going to try to do that here quickly, and hopefully it'll be easy to see. So say we do in purple f times g. So now we're just taking the same domain from negative 2 to 2.5, and we're multiplying values. Now I think some of these might get outside of what's on the graph. Shouldn't be too bad actually. Okay, so we have a y value of 5, we have a y value of negative 1, so we end up with negative 5. 3 times 0 is equal to 0. 1 times 1 is equal to 1. 2 times negative 1 is equal to negative 2. I'm just thinking this through my head, making sure I didn't make any silly mistakes. I sometimes make silly mistakes. but I'm pretty good at catching them. Okay, so 2 times -1 is -2. I'm just kind of checking for symmetry here. 3 times 0 is 0. Okay. Seems to make sense. Now for the x values of 2, I have 3 and -3, which will be like -9. Something right down here. And you could also find it for negative. Yes, we can do the 2.5 values. -4 and 3.5. It's going to be way far off our graph, so I'm not even going to bother. And we end up with a shape that looks kind of like this. And that one continues a little further. This one is an end point though. Hopefully this isn't deceiving with the arrow on this side as x goes to infinity. It doesn't go forever. We have stated our domain. Actually, we should state our domain. Okay, so we ended up with this shape. It's a shape that should be familiar to you. It's a parabola. So we had a linear times a linear, and we got a parabola. That makes perfect sense. So is it easier to do this graphically or algebraically? It's really up to you, but it's a new strategy for you to work on. So the idea is that if you can break up some kind of function into 2 parts, then you can graph it as those 2 parts, whether it's multiplication. So in this case, our functions are actually f at x so this line, what's this line? It has a slope of -2, a y-intercept of 1, and g at x is a slope of 1, and a y-intercept of 1. Okay, so the parabola that we've graphed here, the equation must be there we go. So we can actually graph a parabola by graphing the linear parts of it, the linear factors, and then multiplying the y values. That could be really handy if you were given 2 functions and asked to combine them, to add them, to subtract them, to divide them, and you didn't really know what that function is supposed to look like. Having this point-wise way of graphing it could be really handy. We'll do one more example. So we're given x plus 1 and 2 to the power of x, and asked to find f plus g. So we could find it algebraically simply by doing the addition. F plus g at x is equal to x plus 1 plus, I don't know why, but I like putting the 2 to the power of x first. We don't really know what this function looks like. We haven't studied this function at all. If you were asked to graph this, to graph it based on here, you could use a table of values. It would be a little bit slow. Table of values is like the easiest, most basic method you've ever been taught, right? But you could also just use this graphing method. So I write a little graph here. So because f plus g is made out of functions that we should know quite well, we can graph them. So let me do, I'll do red for f at x. So it crosses at 1 and has a positive slope of 1. Really easy to graph, right? And there were no restrictions on the domain. So it goes forever in this direction. And now let's do g at x. Okay, this is one of the parent graphs, so we should be fairly confident about graphing it. It always goes through this point because anything to the power of 0 is 1. And you always know the point where x is equal to 1, it's equal to the base, because 2 to the power of 1 is 2. And then we know it shoots off crazy fast. Not too worried about the exact values right now. And then we know on this end it has a horizontal asymptote approaching the x-axis. So we can graph that really quickly just because we know a couple of key points and then the general end behavior. And so what does it look like when we add f at x and g at x together? Let's do a couple of points. Let's do it in blue. Okay, so this point's pretty easy. We have 1 plus 1 is 2. 2 plus 2 is 4. Okay, so we had, it goes off really, really quickly for g at x. Now it goes off really, really quickly, plus it's always getting another value that's 1 bigger than the value before. So this is just going to have an even bigger upward slope, and it's going to approach infinity even faster. And then here we have values that are approaching 0 plus the linear value. So it's like we have this red line plus a little bit, plus even less, plus even less, plus even less. So that means these values are getting closer and closer to the line. Okay? And now we found f plus g at x. Without this strategy to break this function into two parts, could you have graphed this all by yourself? You could have done the table of values, but you wouldn't just have a sense of what this graph looks like. In this section, you're trying to learn a strategy for breaking a function down into parts and understanding how those parts interact with each other. So whether they're being multiplied or added or subtracted, just a general sense of when I add two functions together, this is what's going to happen in general. And this is a helpful tool for future units, so you can understand the functions that you're making fairly quickly just by having a general understanding. Well, when I add two together, it would be adding the y values, so it should look something like this. Best of luck!